Since the column is square in shape, the interaction curves for x and z directions overlap. At present, for a normalized PU value of 0.382, the corresponding normalized MU value is 0.012. Now I increase FCK from 15 to 20. The normalized PU reduces to 0.287, and the normalized MU increases to 0.023. Now I increase FCK from 20 to 25. The normalized PU becomes 0.229, and the normalized MU becomes 0.038. At present, the grade of steel Fy is 250. At this point, the normalized PU is 0.127, and the normalized MU is 0.039. The maximum normalized PU is 0.428, and the maximum normalized MU is 0.165. Now I increase Fy from 250 to 415. The working point remains the same, but the maximum PU increases to 0.449. Now I increase Fy to 500. The maximum PU increases to 0.460. So instead of a square section, we can try a rectangular section. Since the calculated MU in x direction is much higher than MU in z direction, I will first reduce the column width in x direction from 400 mm to 300 mm. Now observe the graph. The two interaction curves are clearly separated. Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and a warm welcome back to today's DIY project. You are watching Structural Design Only, a channel with a different vision. The title of today's video is RC Column Design, Short and Long. Automated 3D PU-MU Interaction Curve and Dynamic Excel Logic. Part 4. Excel Presentation. Before we begin, a quick note for non-civil engineer viewers. We will discuss some technical terms today, but please feel free to follow along. Just treat the terms as numbers, and focus on the Excel process. You can use the same logic for your own DIY spreadsheet projects. If you face any difficulty, please mention it in the comments. I will try my best to help you, free of charge. In our previous video, Part 1, we discussed the fundamental theory of short and long RC column design. That episode focused on basic mechanics and calculations, explained through a detailed PowerPoint presentation. Today, in Part 4, we take another step forward towards a fully automated 3D PU-MU interaction curve, developed completely in Excel. Think of this as a practical DIY tool, designed by an engineer, for engineers. If you are new to this channel, I strongly recommend watching Part 1 first, to get a clear foundation. For viewers who want to strengthen their basics even further, my video on column design without SP16 charts is another useful resource. This episode is a continuation of the series on a dynamically interchangeable designing sheet for short and long columns. Once again, we will dive deep into Excel formulas and the methodology behind short and long column design, so that everything remains clear and easy to follow. Alright. Let's jump straight into the next slide. In part 3 of this video series, we paused our journey after explaining the table titled Tables for Column and Condition, K-Factor, Distribution, and Recommendation for K-Value, when the column is an unbraced column. At the bottom of this table, we see two more tables. These are effective moment of inertia and Euler's buckling load capacity, PCR in kilonewton. Both of these tables together form table number 6. The table titled Effective Moment of Inertia has two main parts. The first part is modulus of elasticity of concrete. The second part is equivalent moment of inertia of the column section. Modulus of elasticity of concrete is further divided into two parts. The first is static elasticity of concrete, called EC static. The second is effective elasticity of concrete, called EC-EFF. Equivalent moment of inertia of the column section is also divided into two parts. Equivalent moment of inertia along x-axis and equivalent moment of inertia along z-axis. Now I am selecting the formula for static elasticity of concrete. The formula is 5000 multiplied by square root of FCK. The defined name of this cell is EC. This is a standard formula, so we will not spend more time here. Next, I am selecting the formula for effective elasticity of concrete. If the column is a long column, the effective elasticity of concrete is equal to static elasticity of concrete divided by 1 plus creep value. The defined name of this cell is EC-EFF. If the column is a short column, the effective elasticity remains the same as static elasticity. Now I am selecting the formula for equivalent moment of inertia of the column section in x direction. If the column is a long column, the value is gross moment of inertia in x direction plus net moment of inertia of bars in x direction. If the column is a short column, the value is only the gross moment of inertia in x direction. The defined name of this cell is IEQX. Here, ISX represents net moment of inertia of bars in x direction, and IC gross X represents gross moment of inertia of the column in x direction. Now I am selecting the formula for equivalent moment of inertia of the column section in z direction. The logic is exactly the same as x direction. Only the terms change. IC gross X becomes IC gross Z, and ISX becomes ISZ. The defined name of this cell is IEQZ. Now we move to the next table, titled Euler's buckling load capacity. This is a dynamic heading. If the column is a short column, the heading becomes Maximum allowable compression. If the column is a long column, the heading becomes Euler's buckling load capacity PCR. Euler's buckling load is applicable only for long columns. Since our present column is a long column, we are seeing Euler's buckling load capacity. Now I am selecting the formula for Euler's buckling load capacity in x direction. If the column is a long column, the value is ECEFF multiplied by IEQZ multiplied by pi squared divided by square of effective height in millimeters, and finally divided by 1000, to convert into kilonewton. If the column is a short column, the value shown is Pu. The defined name of the cell is PCRX. Next, I am selecting the formula for Euler's buckling load capacity in Z direction. If the column is a short column, the cell remains blank. If the column is a long column, the formula uses ECEFF IEQX pi squared and effective height. In the same manner as before, the defined name of the cell is PCRZ. Now we come to the dynamic tidal equivalent buckling load capacity. If the column is a long column, the tidal becomes equivalent PCR. If the column is a short column, the tidal becomes axial load Pu. Finally, we come to the formula for equivalent buckling load capacity. If the column is long and braced, the equivalent buckling load is the minimum of PCRX and PCRZ. If the column is long and unbraced, the equivalent buckling load is 0.75 times the minimum of PCRX and PCRZ. If the column is a short column, the value shown is Pu. In today's world of shorts and reels, I honestly don't know how many of you will stay with me till the end of such a detailed session. But I truly believe this half knowledge can mislead, while complete understanding empowers. That is why I always choose detail over shortcuts, even if only a few committed learners are watching. If you've stayed till here, thank you from the bottom of my heart. Your time, patience, and trust truly matter to me. And now yes, it's time to perform a small YouTube ritual. Now, if you find this material helpful and informative, please give this video a big thumbs up. Sharing knowledge is the best way to enhance it. If you have colleagues or engineering friends who would benefit from this, please share the link with them. If you would like to support my honest effort in creating these tutorials, please subscribe to the channel. If you feel any part of the explanation was weak or unclear, please use the dislike button without hesitation, but always share your reason in the comments. Sometimes disliking is more valuable than liking, because feedback helps us improve. A dislike without context, however, is a verdict without judgment. Finally, consider a contribution, whatever fits your budget, without any pressure. You'll find the link in the description below. Thank you for your cooperation and support. With this explanation complete, we now shift our focus from table number 6 to table number 7. Now we are on table 7. Within this table, we have 3 subtables. The title of the first table is Calculation for number of bars in tension and compression in the column, X direction. The title of the second table is Calculation for number of bars in tension and compression in the column, Z direction. And the title of the third table is Moment magnification for long or slender column design. As we know, to convert a long or slender column into an equivalent short column, we need to magnify the moments in both directions. The first 2 tables are similar in nature. So, I will explain the first table and the third table in detail. To save some time, I will leave the second table for my viewers to go through. Now, let's start with the explanation and formulas for the first table of table number 7. In this table, the bars are arranged from right to left, only for the convenience of calculation. The column numbers and bar quantities are taken directly from table number 5, which was explained in the previous episode. That table is titled, Radius of gyration of bars in X-axis and Z-axis, total MI of bars, and gross MI of the column section. For calculations along the X-axis, values are taken from the table titled Calculation of MI for bars and gross MI of the column in Z-axis. Similarly, for calculations along the Z-axis, values are taken from the table titled Calculation of MI for bars and gross MI of the column in X-axis. Explaining these rows again will only waste time, so let us move directly to the important part. In the third row of both tables, you will find the distance of bars from the right edge, in X and Z directions. Now, for the first column. If the column number cell is blank, the value is 0. Otherwise, it equals the effective cover. The distance between the first and last bar rows is divided into 5 equal spacings. For the second column, if the column number cell is blank, the value is 0. Otherwise, the value is effective cover plus column number minus 1 multiplied by bar center to center spacing in X direction. This formula is copied to the remaining cells. Since 12 bars are selected in the Z direction, we get 2 columns with 6 bars each, and 6 rows with 2 bars each. Now, we calculate the neutral axis for the strain diagram. Neutral axis along the X direction, XUD, is 700 multiplied by effective depth in X, divided by 1100 plus 0.87 multiplied by Fy. And, neutral axis along the Z direction, XUB, is 700 multiplied by effective depth in Z, divided by 1100 plus 0.87 multiplied by Fy. Next, we calculate the compressive strain in steel bars. If the column cell is blank, or the distance of the bar from the right edge is less than XU, the strain value is 0. Otherwise, the strain is 0.0035 multiplied by 1 minus distance divided by xu. The same type of formula is applied in both x and z directions. Now, compressive stress, FSC, in steel is calculated as steel stress, FSC, equals modulus of elasticity of steel multiplied by strain value. Next, compressive force in steel, CS, per column. Steel stress, FSC, multiplied by number of bars, multiplied by area of one bar. Next, it is compressive force in concrete, CC, is 0.36 multiplied by FCK, multiplied by breadth, multiplied by XU, divided by 1000. Total compression in the column is the sum of compression in concrete and compression in steel. Now, we count the number of bars in tension. Bars having zero compressive strain are considered as tension bars. The Excel logic used here is: if the strain value is 0, that bar is excluded from the count. Otherwise, the corresponding bar number is added. Next, area of tension bars is calculated by multiplying number of tension bars with area of one bar. The same formula is applied for both x and z directions. Now, we calculate the resultant steel force in tension. Resultant steel force equals 0.87 multiplied by Fy multiplied by area of tension steel divided by 1000. This formula is used for both x and z directions. Next, net axial load capacity, PB, is calculated as compression in concrete plus compression in steel minus tension in steel. Same procedure is followed for both directions. Now, we calculate the reduction coefficient, Ka. For a short column, the reduction coefficient, Ka, is not applicable. For a long column, the coefficient, Ka, is calculated only when the value lies between 0 and 1.14. Otherwise, the value is marked as not applicable. The same logic is used for both x and z directions. Finally, we calculate the moment magnification, MU_mag, which is one of the most important steps in long column design. For a short column, the magnified moment is taken as the maximum of absolute value of applied moment, or absolute value of axial load, multiplied by 20, divided by 1000. For a long column, when the reduction coefficient is valid, the magnified moment is absolute applied moment plus absolute value of reduction coefficient multiplied by additional moment. Otherwise, the value is not applicable. Alright. Let's jump straight into the next table, table number 8. Now we are on table number 8. Table 8 and Table 9 are the base tables for developing the three-dimensional interaction curves for PU and MU, in X direction and Z direction. Before going deeper into these tables, let us first observe how the three-dimensional interaction curves behave. Alright. Now I am switching to table number 1. Now we are on table number 1. On the right side of this table, the three-dimensional interaction curves are already superimposed. The grade of concrete FCK is 15 Newton per square millimeter. The grade of steel Fy is 250 Newton per square millimeter. This value is used only for comparison, not for new construction. Column depth in X direction is 400 mm. Column width in Z direction is also 400 mm. Bar diameter is 12 mm. Number of bars is 12. Bar distribution is equal. Since the column is square in shape, the interaction curves for X and Z directions overlap. At present, for a normalized PU value of 0.382, the corresponding normalized MU value is 0.012. Now I increase FCK from 15 to 20. The normalized PU reduces to 0.287, and the normalized MU increases to 0.023. Now I increase FCK from 20 to 25. The normalized PU becomes 0.229, and the normalized MU becomes 0.038. Now I increase FCK to 45, the maximum value in this list. The normalized PU becomes 0.127, and the normalized MU becomes 0.039. So we clearly observe that, with increase in FCK, the PU ratio decreases, and the MU ratio increases. Now, let us observe how the grade of steel affects the three-dimensional PU and MU interaction. At present, the grade of steel Fy is 250. At this point, the normalized PU is 0.127, and the normalized MU is 0.039. The maximum normalized PU is 0.428, and the maximum normalized MU is 0.165. Now I increase Fy from 250 to 415. The working point remains the same, but the maximum PU increases to 0.449. Now I increase Fy to 500. The maximum PU increases to 0.460, while the maximum MU remains unchanged. Now I increase Fy to 550. The maximum PU increases to 0.466, and MU remains constant. Now I increase Fy to 600. The maximum PU slightly reduces to 0.442, while MU still remains constant. So we conclude that, with increase in steel grade Fy, the axial load capacity Pu increases, but the moment capacity Mu remains almost constant. At present, in the table titled "Check for calculated and available moments," we can see that the maximum available mu in x direction and mu in z direction are both equal to 113 kN/meter. The calculated mu in x direction is 66 kN/meter, and the calculated mu in z direction is 18 kN/meter. So the design is safe. But both calculated moments are much lower than the available moments. This clearly indicates an over-designed section. In this case, the ratio of calculated moments in x and z directions is quite different. So instead of a square section, we can try a rectangular section. At present, the column size is 400 by 400 mm. Since the calculated mu in x direction is much higher than mu in z direction, I will first reduce the column width in x direction from 400 mm to 300 mm. Now observe the graph. The two interaction curves are clearly separated. The black dotted curve represents the x direction interaction, and the red dotted curve represents the z direction interaction. The blue horizontal line represents the current normalized ratio of Pu. For a given design, the normalized ratio of Pu remains constant, and it is common for both directions. However, the normalized ratios of mu in x and z directions are now different, because the section is rectangular. From the graph, we can see that the maximum available normalized ratio of Pu is well within the interaction curves in both directions. Hence, the column is safe. This clearly shows how changing a square section into a rectangular section helps in separating the interaction curves and achieving a more efficient design. Let's move to the table number 8. Once again, we are on table number 8. Table 8 and table 9 are, more or less, similar to table number 7. In table 7, we calculated the compressive and tensile forces in steel based on the design load and moments, by considering a single stress block in both x and z directions. Here, however, we need to assume several stress blocks and study their combined effect. Before moving further, I would like to highlight a very valuable comment from one of my viewers. Mr. T. N. Murthy wrote that, this topic of column interaction curves is continuing for several episodes, and he raised an important question whether it is practical to complete this topic spread across many videos. I truly appreciate this feedback. In fact, I have been thinking the same. At this point, the duration of this video has already crossed 30 minutes. If I explain all 11 tables in detail, this single video may easily extend beyond 3 hours. That may not be practical for most viewers to follow continuously. So, for now, I am intentionally skipping the detailed explanation of the remaining tables. If even 10 genuinely interested viewers request me in the comments to explain the remaining tables step by step, I will definitely do that in a separate follow-up video. For the moment, let us move ahead to the final testing of this Excel design sheet. At present, we are on the dashboard of our designing sheet. This is also the first table of this Excel sheet. Here we can see the title: Short Column Design by Stress Block and Axial Load with Biaxial Moments with 3D Interaction. The unsupported length of the column is 3 meters. The ratio of unsupported length to the minimum lateral dimension is less than 12. Therefore, Excel identifies this column as a short column. And we are seeing this title. This is a dynamic title. When Excel identifies the column as a long column, the title will automatically change. Now, let us see this change. I am increasing the unsupported length from 3 meters to 3.5 meters. Now, the title changes to Long Column Design by Stress Block and Axial Load with Biaxial Moments with 3D Interaction. With the selected parameters, both short column and long column designs are showing OK. Now, I am undoing this change and returning to the short column condition. Next, follow the table titled Selected Load and Moments. These loads and moments are taken from the table Loads on Column. This table automatically selects the governing design load. Now, returning once again to the dashboard. The selected loads and moments shown here are the initial factored load and moments. Next, follow the table titled 01 Design Loads for Short Column. This is also a dynamic title. When the column becomes a long column, it will automatically change to 02 Design Loads for Long Column. Since the present column is a short column, the factored axial load Pu remains equal to the initial Pu, which is 1100 kN. The factored moment around the x-axis, selected and design values, is 50 kN-meter. However, the selected factored moment around the z-axis is only 4 kN-meter, while the design moment around the z-axis is 22 kN-meter. This difference is due to the provision for minimum eccentricity as per IS 456/2000. In this case, the selected z direction moment is less than the minimum required moment. So Excel automatically adopts the minimum moment value. We have already seen the 3D interaction in x direction and z direction. So I am skipping that portion here. Now, let us move to the table titled Checklist for Final Design. Here we are checking the percentage of steel provided, minimum clear spacing of bars, and buckling load. Buckling load check is applicable only for long columns. For long columns, Excel verifies whether the buckling load is greater than the axial load Pu. Next, we are checking the design moments. For short columns, the design moments remain the same as shown in the design load table. For long columns, these moments will be replaced by magnified moments. Once again, buckling load and moment magnification convert a long column into an equivalent short column. Below this, we can see the check for uniaxial moment capacity. For uniaxial bending, the interaction ratio must be less than or equal to 1. The present value is 0.299, which is acceptable. Now, let us observe the available moments from the 3D PU and MU interaction. In the x direction, the available MU is 119.01 kN/m. In the z direction, the available MU is 50.30 kN/m. Now, I am reducing the concrete grade FCK from 45 to 25 Newton per square millimeter. As a result, the available moments reduce to 27.03 and 11.12 kN/m. These values are less than the design moments of 50 and 22 kN/m. Hence, the design is not okay. Next, I am increasing the depth dx from 300 to 325 mm. Still, the available moments are less than the design moments. So the design remains not okay. Now, I am increasing the width, BZ, from 400 to 500 mm. Now, the available moments become 86.25 and 23.64 kN/m. These values are greater than the design moments. Hence, the short column design is okay. Next, I am testing the effect of steel grade and area of steel provided. First, I am changing the steel grade Fy from 600 to 415 Newton per square millimeter. The design is still okay. Next, I will test this sheet by converting this column into a long column. Let us continue our journey. After testing the column as a short column, now I am going to test the same column as a long column. We already know that a column is considered as a short column when the ratio of unsupported length to the minimum lateral dimension is less than or equal to 12. Yes, this is universally true, but only for a column with fixed end condition and a braced system. End condition and braced or unbraced condition can convert a column from a short column to a long column. Now the question is, how? Below the column dimension table, we have another table titled Joint Condition of Column. In this table, we have two drop-down menus. In the first drop-down menu, we have 5 end condition options. 01 fixed end. 02 fixed pinned end. 03 pinned end. 04 fixed roller end. And 05 pinned roller end. Below this, we have another drop-down menu with 2 options. 01 braced and 02 unbraced. The combination of these two selections decides whether the column behaves as a short column or a long column. In both drop-down menus, options with higher numbers push the column toward long column behavior. At present, we selected fixed pinned end and unbraced condition. Under this combination, Excel identifies the column as a short column, and the design is safe. Now, I am changing the end condition from 02 fixed pinned end to 03 pinned end, keeping the column unbraced. Look carefully. Now the column is no longer a short column. It is classified as a long column, and the present design is not safe. Next, I change the condition from unbraced to braced. Look again. Once more, the column becomes a short column, and the design is safe again. I believe, all of you have now understood how a column changes from a short column to a long column, and vice versa. After completing the demonstration of short column design, and showing how a column changes from short to long and long to short, our next target is the design of a long column. In the previous section, we designed a short column using the following basic parameters. Concrete grade 45. Steel grade 415. Unsupported height 3 meter. Depth dx 300 mm. Width bz 400 mm. Clear cover 40 mm. Joint condition selected as fixed pinned end and braced. Creep coefficient selected as 3 severe. The factored load Pu is 1100 kN. Initial moments are MUX 50 kN and MUZ 4 kN. With these inputs, the column is classified as a short column, and the design status is OK. Now, I change the joint condition from fixed pinned end to pinned end, and also change the condition from braced to unbraced. Now the column becomes a long column. Look at the table titled, Design Loads for Long Column. Here, the magnified moments have changed. MUX magnified becomes 120 kN, and MUZ magnified becomes 66 kN. These magnified moments are required to convert the long column into an equivalent short column. Now observe the available moments from the three-dimensional PU-MU interaction curve. They are 119 and 50 kN, which are less than the required magnified moments. That is why the final message shows check long column design. Now observe the buckling load. It is 1570 kN. Buckling load must always be greater than Pu, which is 1100 kN. Now the question is, why should the buckling load be greater than Pu? Because buckling load separates column behavior from out-of-plane failure and keeps the design within in-plane behavior. In-plane failure is more predictable than out-of-plane failure. This condition is satisfied, but the margin is not very high. We already know that buckling load depends on the creep coefficient. Currently, the creep coefficient is selected as 3 severe. This is the maximum value. Now I change the creep coefficient from 3 severe to 0 short term. Observe the buckling load. It increases significantly. This option is generally used only for testing or temporary structures. Next, I change the creep coefficient from 0 short term to 1 moderate. The buckling load reduces, but it is still within a safe range. In practice, most engineers prefer 2 long-term creep coefficient. So I select 2 long-term. The buckling load reduces further, but remains acceptable. Now observe MUX design and MUZ design. Both values are less than the magnified moments. So this check is OK. Next, look at the uniaxial moment capacity ratio. The value is 0.841. Since it is less than 1, this condition is also OK. Now I reduce the concrete grade from 45 to 25, which is commonly used in practice. I also increase the section size to depth 400 mm and width 500 mm. Now a minor issue appears related to minimum percentage of steel. So I reduce the number of bars from 12 to 8, and increase the bar diameter from 12 mm to 16 mm. Now observe the final message. Long column design OK. Now, I am going to demonstrate how unsupported length can change a column from short to long, or from long to short. Next, I change the joint condition to fixed end and braced. This is one of the most common conditions. Now the column becomes a short column again, and the design is safe. Finally, I demonstrate the effect of unsupported height. I increase the height from 3 meter to 7 meter. The column is still short and safe. At 9 meter height, the column becomes long and unsafe. When I reduce the height to 8 meter, the column is long, but the design becomes safe again. Generally, we think that only the unsupported length converts a short column into a long column. But this is only one reason among several reasons. End condition, braced, unbraced condition, creep coefficient, and load, moment interaction also play a major role in transforming a column from short to long, and from long to short. With this, I am finally concluding short and long column design in Excel. Honestly speaking, I am stopping here not because I want to, but because I have to. The video has already crossed almost 1 hour. My mind says, enough for today. But my heart keeps whispering, just explain a little more. Sometimes, while recording, I feel like I am speaking to a very long wall. Hoping that somewhere, someone is listening, learning, and nodding quietly, somewhere on the other side. If this video helped you, even a little, please press the like button. That small click tells me, I am not talking alone. Sharing knowledge is the only way knowledge grows. So please share this video with your colleagues and fellow engineers who might need it. If you believe in honest, detailed, step-by-step learning, then subscribing to the channel is the strongest support you can give me. Let us grow this learning community slowly but meaningfully. And yes, if you wish to support me financially, you will find my UPI link in the description. Do not worry. It is never about the amount, only about the encouragement. Finally, if you felt any part of this explanation was weak, confusing, or unnecessary, please do not hesitate to use the dislike button. But I request one thing. Tell me why in the comments. Because sometimes, a thoughtful dislike teaches more than a silent like. A dislike without a reason, however, is just silence in another form. Thank you for staying with me, till the very end. Take care, and stay connected with me in the journey ahead.